Good morning, all of you. Uh, so already we have started the field compaction control. Okay. In field compaction control, we have studied the calcium carbide method or speed test method. How can we calculate the water content in a very short period in the field? We have seen one video was in our earlier class. So next, the method of field compaction control. Next method of field compaction control is your the Proctor needle method. Okay, Proctor needle and calibration curve you can see in the this slide. The next method is Proctor needle method. Just I want to say something about this method, then we can see one video. What is the Proctor needle method? Just I am discussing. 1 minute. Okay, so the Proctor needle method. Actually, this method is commonly very common. The Proctor needle consists of needle point and wait, the Proctor needle consists of a needle point attached to graduated needle shank, which in turn is attached to a spring-loaded plunger. The needle point of varying cross-sectional area are available so that a wide range of penetration resistance can be measured. And the penetration force is read on loaded gauge fixed over the handle. And in this figure, you can see this kind of instrument normally is used to measure the dry density and as well as the penetration value. Normally we get the penetration value through this Proctor needle test, and this penetration value we can calibrate with the our dry density. One video is there. If you see one video, then it will be clear to you. But the method normally based on the penetration value. Okay, this is the instrument which is normally we are used to penetrate, and we are getting some penetration value. We are normally we are apply this penetration value or resistance value with calibration chart, and the density will come when we calibrate with the calibration chart. So normally this instrument is used to penetrate. Okay, that's why the name of this instrument is Proctor needle test or the Proctor penetration test. Okay, to use the needle in the field, a calibration curve and the calibration curve is plotted in the laboratory between the penetration resistance as the ordinate and the water content as the abscissa. Okay, this curve is there, one chart is there, dry density versus water content and penetration resistance. Okay, so penetration resistance, these values are available in the field. We can get the values of penetration resistance from the field, because this using this instrument the penetration resistance values are available. And when penetration resistance values are available, we can get the dry density value of the soil as well as the water content through calibration chart. Simply one calibration chart is there. Whatever your penetration resistance, and if you have the penetration resistance value, then easily you can calculate the dry density and water content. Okay, these are the field tests. Normally we are applied this kind of test for field only. The penetration resistance corresponding to various water contents are thus noted at the end of each Proctor compaction, and a calibration curve is plotted. This curve may be used to determine the placement water content. The penetration resistance of the compacted soil in the field is determined with the Proctor's needle, and its water content is read off from calibration curve. So this type of test normally we are performed in field. Just I have one video. Just wait, I am showing you the video. Then the things will be clear. So this is one kind of penetration resistance value test, or the Proctor needle test in the field. You can see this kind of instrument normally used in the field to find out the penetration resistance value, and from the penetration resistance value we can calculate the dry density as well as the water content. Okay, normally this penetration resistance value indicates the dry density value. This is the one kind of very simple correlation, okay, with your soil condition. From your soil condition you can identify the dry density and water content state of the soil.
So you see how many strikes it takes to get to the next one.
So normally the uh, number of stroke, number of penetration value are needed to be note down. Okay, so then we can calculate the actual penetration resistance. So in our syllabus, normally in our undergraduate syllabus, this description of the test is important. How can we calculate the value of penetration resistance or dry density and water content is not available, and as well as not important for the study. Just the what is the test, what is the Proctor needle. uh, the question may come regarding, suppose, what are the methods are used for field compaction control, what is the Proctor needle method, and what purpose it is used. Okay, and with this figure, if you asked to about the Proctor needle test, you should mention all the things with this figure, all the description with this figure. What is Proctor needle, what is the use of the Proctor needle. Okay, so normally this kind of tests are normally performed to find out the penetration resistance, and when the penetration resistance is available to us, we can calculate the dry density as well as the water content of the soil from the calibration chart. So this is the your field compaction control methods. One is already I have discussed in the last class, the this method already you have seen this, the calcium carbide method or speed test method to determine the water content in the field. This is one of the quick method, and another method is this Proctor needle method to find out the dry density water content through penetration resistance of the soil. But this method is uh, very common method, this Proctor needle method, and it is used generally. This method is maximum. This method is used in the field to find out the water content and dry density. Okay, uh, and these are total of your field compaction control. Now the next is the factors affecting compaction. Okay, factors affecting compaction. The various factors which affect the compacted density, like water content, amount and type of compaction, method of compaction, type of soil, and addition of admixture. Sometimes we add admixtures. I think all of you have some idea what is admixture. Already in concrete technology you have studied about the admixture. Additive materials, normally when we add some additive materials to the uh, our actual material which is used for construction, or which my parent material actually, when we are add extra material to gain the strength, to gain something for which is advantage for my construction, advantage which is need for me, or which can be increase something, okay, or decrease something, such type of additive materials we can say admixture. So factors affecting compaction can be measured by number of way. Suppose one is water content. Water content, one is the factor affecting compaction under this, and number two, amount and type of compaction, third, method of compaction, four, type of soil, and five is the addition of admixture. Okay, so you should keep in your mind always the water content, amount and type of compaction, method of compaction, type of soil, and addition of admixtures. Okay, so first if we talk about the water content, it has been seen by laboratory experiments that as the water content is increased, the compacted density goes in increasing till a maximum dry density. is achieved, after which further addition of water decrease the density. Actually, I am talking about this graph. From this graph, it is clear to us that it has been seen by the laboratory experiment that as the water content is increased, the compacted density goes on increasing till a maximum dry density is achieved, after which further addition of water decreases the density. It is uh, completely true for the standard Proctor test or any compaction characteristics test. Uh, this type of statement is completely true for our soil. When only a relatively small amount of water is present in soil, it is firmly held by the electrical forces at the surface of soil particles with a high concentration of electrolyte, which prevents the diffuse double layer surrounding the particles from developing fully. This is the physics. What is the physics? Physics is that when only a relatively small amount of water is present in soil, it is firmly held by the electrical forces at the surface of soil particles with a high concentration of electrolyte, which prevents the diffuse double layer surrounding the particles from developing fully. Okay, this is the physics. The double layer depression leads to a low interparticle repulsion, and the particles do not move over one another easily when compacting energy is applied, and hence high percentage air voids and low density is achieved. The increase in water content results in an expansion of double layer and reduction in the net attractive forces between particles, or in increased interparticle repulsion, which permits the particles to slide more easily past one another in a more oriented and denser state of packing together, and hence higher density. After the optimum water content is reached, the air voids approach approximately a constant value, as a further increase in water content does not cause any appreciable decrease in them, even though a more orderly arrangement of particles may exist at higher water contents. The total voids due to water and air combination go on increasing with increasing of water content beyond the optimum, and hence the dry density of the soils fails. So this is the actually basic physics normally which happens in the soil particles when we add the water with soil particles. Due to this electrolyte concentration of electrolyte, normally first soil gives us the maximum density at a certain percentage, up to a certain percentage, and after that when it is achieved the maximum density at certain percentage, if we add further water with soil, then it will give us the lower percentage. So this is the basic physics behind this water content and soil. Okay, but as an engineer, and, as an engineer or in practice, normally we follow the whatever I have shown you in the last class, the your the about the test. Actually this test is very important to us as a in soil mechanics. Normally soil test, first test in soil normally which we are preferred the test, that is standard Proctor test, because through standard Proctor test only we can find out the density of the soil or maximum density of the soil, and water content, at which water content it will give the maximum density. Because when water content known to us, sorry, optimum moisture content is, or optimum water content is known to us, and maximum dry density is known to us, then with using this water content, normally this optimum moisture content, we normally prepared all the sample in the lab. Okay, because number of tests are required to get the number of values, because already in soil mechanics 1 you have studied about types of soil: clayey soil, highly clay, medium clay, poor clay, well graded sand, then poorly graded sand. Okay, Even your silty clay, organic clay. So lots of characteristics of soil you have studied in the your soil mechanics 1 part. So that's why number of tests also we have to be carried out in the lab. But when it is possible, when we can because dry soil cannot be performed, okay. So to perform all the tests we have required some water content that which we can add with the soil. So this water content, where we can get this water content? We can get this water content from the standard Proctor test. Okay, this optimum moisture content. So my intention of the saying these things that the water content, the physics behind of the water content, or the how water content changes the all the things, this phenomena, first increasing then decreasing phenomena, this is totally physics, but actually we grab the idea or grab the logic. Okay, the logic normally we apply the we take the application of this physics. We take the application of the physics, but you can read from any of the book, soil mechanics book, what are the factors, what are the physics behind water content. Okay, you can study. Already I have dictated that the electrical forces at surface of soil body with high concentration of electrolyte, which prevents the diffuse double layer surrounding the particles from developing fully. This is the physics, basic physics of water content. You can study any book, no problem, but the application is the most important to us. How can we calculate the optimum moisture content? Number 2, amount of compaction. The amount of compaction greatly affects the maximum dry density and optimum water content of a given soil. The effect of increasing the compacting energy results in an increase in the maximum dry density and decrease in optimum water content as shown in figure. Uh, However, the increase in maximum dry density does not have a linear relationship with increase of compacting effort. So normally, again I am repeating, the amount of compaction greatly affects the maximum dry density and optimum water content of a given soil. The effect of increasing the compactive energy results in an increase in a maximum dry density and decrease in optimum water content. We can see from this figure. However, the increase in maximum dry density does not have a linear relationship with increase of compactive effort. So normally always we test our soil uh, through through standard Proctor test. We can identify the OMC and MDD value, OMC optimum moisture content and maximum dry density value of our soil. Now when we construct or suppose in road construction, normally what we do, normally first we laid the soil. Okay, laid the soil and start the rolling. This is the first stage. When we perform this rolling or the compacting process, at that time always we should check that our soil is compacting properly, or soil is uh, our soil is with the exact amount of water content which I have calculated as a OMC in the lab. Okay, so in the field always during compaction, always we should follow that the water content is we should follow the water content, or we should maintain the water content in the field which I have tested as OMC, optimum moisture content, in my laboratory test. Okay, so OMC values always should be maintained, because if we during construction, if we maintain the this OMC value in the field, then always our soil will give the maximum dry density or maximum density. Okay, when my soil will give the maximum density, I can put the maximum load. or I can construct as per my design load on the field. So in the construction field, always we maintain this optimum moisture content value during rolling, during compacting, whatever, maybe in the building, maybe in construction of the building, maybe construction of the road. Always we maintain the OMC value. In the high project cases, normally always we should maintain, because if we maintain this OMC value, then only my soil will give the required maximum dry density, or which I have tested in the laboratory, the maximum dry density value. Also, this amount of compaction, also one of the the factors affecting compaction, but there is no relation between the amount of compaction is directly related to your dry density and water content, whatever. But amount of compaction, one of the factor which maintain this dry density and water content. Okay, as we seen in the lab, suppose our standard Proctor test, we always we have given blows that 25 blows for each layer in the standard Proctor test. From this reference, you can see how also here the water content versus dry density graph. Suppose first this graph for 10 blows. If we taken 10 blows, okay, it will give us such type of nature. The curve nature is like that. If we take the 15 blows, okay, 15 blows in the test, 15 blows, this will give us such type of figure. If we take 20 blows, okay, for test, then it will give such type of nature of the curve. If we take 25 number of blows, then it will give the this type of curve. Okay, this will show this type. So from these blows, number of blows, it is clear to us that 25 number of blows always give us the better result, always better result, and optimum moisture content and dry density. But if we increase these blows, if we increase these blows, then also we can get this type the maximum result, maximum dry density, and the optimum moisture content value. But this 25 blows, it is seen that this 25 blows is the appropriate for any standard construction. Okay, any standard, for any standard building, for any standard road, this 25 blows test is appropriate, and the values which are we got from the standard Proctor test, that is optimum for moisture content as well as the maximum for dry density. So this type of curve can be described that the effect of compactive effort on compaction obtained by the, this is a Jodhpur mini compactor, so one of the another test, no problem. So this compactive effort or compaction we described by flows, uh, always the dry density and water content will be increase. Okay, when the compactive effort and number of blows will increase. Next, method of compaction. The density obtained during compaction for a given soil greatly depends upon the type of compaction or the manner in which the compactive effort is applied. The various variables in this aspect are weight of the compacting equipment, the manner of operation such as dynamic or impact, static, kneading or rolling, and the time and area of contact between the compacting element and the soil. Again, the density obtained during the compaction for a given soil greatly depends upon the type of compaction or the manner in which the compactive effort is applied. The various variables in this aspect are weight of the compacting equipment, the manner of operation such as dynamic or impact, static, kneading or rolling, and the time and area of contact between the compacting element and the soil. Next is type of soil. The maximum dry density achieved corresponding to a given compactive energy largely depends upon the type of soil. Well-graded, coarse-grained soils attain a much higher density and lower optimum water contents than fine-grained soil, which require more water for lubrication because of the greater specific surface. And a figure show this figure shows dry density water content curves for a range of soil types. In general, coarse grained soils can be compacted to higher dry densities than fine grained soil. So there are lots of type of soil and there this water content dry density value curve. Okay, so this is the oil graded gravel, this is oil graded sand, this is poorly graded or uh, medium graded silt. This is the clay. This is also high organic clay. Okay, this is a low organic clay. This is a medium organic clay or silt. So this kind of figure can be, this kind of curve can be seen for different soil. Okay, different types of soil we can see different kind of graph or different type of curve of water content dry density value. Next is compaction curve for cohesionless sands. In the case of cohesionless soils which are devoid of fines, the water content has very little influence on the compacted density. For such soils, the dry density decreases with an increase in the water content. In the initial stage of the curve, particularly under a low compactive effort. This is the typical compaction curve for cohesionless sand. Cohesionless means sandy soil. Okay, sand. For sand, if we perform sand, this standard Proctor test for sand, okay, compaction characteristics test for sand, then what will give the curve? Sometimes in any competitive exam interview, some any interview you can be asked, not any college campusing interview, in government interviews you may be asked what would be the nature of the curve for sandy soil. Normally we are perform this test in your cohesive soil. Normally cohesive soil is important for this standard Proctor test. Normally always we perform the test for cohesive soil because as we know the sand has already the load carrying capacity of the soil is maximum. Okay, load carrying capacity of the soil is always sand is always maximum because sand can carry maximum load. But the sand is cohesionless, no cohesion, adhesive factor is there. But in your cohesive soil, okay, cohesive soil, suppose clay type soil, they have adhesion factor or cohesive value. And normally we are perform the standard Proctor test for cohesive soil in our lab, but for sand we are not perform because already sand has the maximum load carrying capacity. Okay, maximum load carrying capacity. Phi value is maximum for sand, C value is 0, and for clay phi value is 0, C value is maximum. Okay, C is the cohesion value, phi is the angle of internal friction. Okay, so for sand angle of internal friction value greater, and that's why sand takes lots of load and can take maximum load in its case. In case of cohesionless soils which are devoid of fines, the water content has very little influences on the compacted density. For such soils, the dry density decreases with an increase in the water content. In the initial stage of the curve, particularly under a low compactive effect, this is due to the bulking of sands, wherein the capillary tension resists the tendency of soil particles to take a dense state. In other words, the capillary tension developed in the sandy soil is not fully counterattacked by the compacting effort, and this capillary tension holds the particles in a loose state resisting compaction. It is interesting to note that the same soil in air-dried or oven-dried condition achieved greater density under the same compacting effort. So without adding water, okay, without adding water in air-dried or oven-dried condition, if we compacted the sand, sand achieves greater density under the same compacting effort. If we add water, it will take low compacting sorry it will achieve low density if we add water, and without water normally sand is achieved greater density under same compacting effort. Okay, the maximum bulking occurs at water content between 4 to 5%. On further addition of water, the meniscus is destroyed and the soil particles are able to shift to take a closer packing, resulting in increase in dry density. The density reaches the maximum value when the cohesionless soil is fully saturated. On further addition of water, the dry density again decreases. Also, so here one another matter is there. The saturation level we can maintain mm, to provide or to getting the maximum load from the soil, load carrying capacity of the soil or density of the soil, but it is more difficult, normally very difficult to achieve such type of stage normally for sand. Okay, and sand itself, it is able to take lots of load, more load than any soil, but we can also achieve the density or a measurable density towards high, then only it is possible if we add some water with very difficult case, actually very difficult case to maintain such type of density for sand. Okay, and if we add maximum water, sometimes if we add maximum water, then normally what happens, the segregate the particles from each other, and it is very difficult then to apply the load on the soil. So sand can take load, no problem, but if we maintain water properly, then only it is possible. Without maintaining proper water content in the sandy soil, normally sand, it is not possible to gather maximum density. But my suggestion is that the sand itself without any water can take maximum load. If we can confine our sand or sandy soil, then it will take maximum load. Suppose any uh, confined container, you can see any confined container, if you fill with sand, then it can take maximum load. Okay, but in a open space we put some sand, and if we apply the load on it, then easily it can segregate. Okay, so that's why in the confined condition normally sand can take maximum load, or it can achieve maximum density. There is no doubt about that. So also the maximum density attained under full saturation, it is not very much higher than that corresponding to air dried or oven dried conditions. Secondly, the attainment of maximum density at full saturation is not due to lubrication action of water, but rather it is due to the reduction of effective pressure between soil particles by hydrostatic pressure. Such soils do not display distinct optimum water content. So normally in this figure, this condition is air dry, this condition is bulking effect, and this is the fully saturation condition. From the this graph point of view, I can see the air dried condition soil will gives average density. Sandy soil or sand gives us the average density. Bulking condition, it will give us the lower density, and fully saturation condition sand will give us the maximum density. But my suggestion is the air dry condition, normally in construction practice, this air dry condition is our objective to achieve the maximum density of the soil, because this fully saturation condition is very difficult to maintain for sand. Okay, because sand cannot hold the water. It always normally no capacity to hold the water, because it has no lubrication effect. There is always some percolation, there is always some lots of voids are there in the sand. Therefore this fully saturation condition is very difficult to maintain for sand. Normally we maintain this air dry condition or dry condition. That's why the soil can or sand can take maximum load in the field. Second is compaction curve for fat clay. Okay, there is another figure, just wait. Hmm. Okay. Uh, this figure shows a typical compaction curve for a fat clay. Here also we see that there is initial decrease of dry density at lower water content. This is the characteristics features of black cotton soils. Okay, highly swelling clays and some fat clays. The optimum water content for such soils range between 20 to 25%. So normally this position is air dried condition. This is same oh, sorry. Hmm. Same this is the bulking effect or partially saturated, we can say, and this is the fully saturation condition. Same for clay. Here this is the air dried condition, this is the your partially saturated condition, and this is the fully saturated condition. And this is the black cotton soil. The load carrying capacity of the black cotton soil is very less. These black cotton soils are available in Andhra Pradesh, Maharashtra, some middle part of India, in central part of India. These black cotton soil are available. The load carrying capacity of the black cotton soil is very less. Okay, even expensive soil. Expensive soil means Multani soil. You know, I think Multani soil. Ladies are normally used for their makeup. Multani soil also the expensive soil. Okay, the fat clay. This is also fat clay, Multani soil. Even Multani soil, this black cotton soil, these are the fat clay. And the load carrying capacity of this kind of soil are very less. Okay, and for this fat clay, normally we can see such type of curve, water content density curve. Addition of admixture. The addition of admixture. The compaction properties, characteristics of a soil can be modified by a number of admixtures other than soil material. These admixtures have special application in stabilized soil, construction, and the addition of admixture is not in your syllabus, but um, uh, but using these admixtures, additive materials, we can increase the density of soil. Suppose as an example, using lime, using cement, using fly ash, we can increase the strength or increase the density of the soil. There are lots of the admixtures in our environment. Some are waste material. Using some waste material also we can increase the density of soil. Normally in highway construction, suppose in this Durgapur Panagar road, already I don't know you have seen or not during construction. Those have seen during construction Durgapur Panagar road, they have used fly ash during construction. They have added fly ash during construction to increase the density, because if we add the certain percentage of fly ash with soil, the soil will give the maximum density. Okay, so this is all for today. Just wait, I am taking attendance. Okay, thank you. Acha, today I will send the Google quiz. All of you please attend the Google quiz, and I think by tomorrow you should give the answer. You you have to solve by tomorrow. Thank you. You can leave.